start.
Okay. Hello, everyone. This is my work about upscaling, casting, and milling of manganese aluminum carbon alloys. I will do first an introduction, then I will show you how the treatment of the material is going to be, the results, and finally I will end with a summary. I will start with the motivation. What's the motivation of this work? The world of permanent magnets is dominated by the rare earth market. And as you can see, the rare earth magnet market is dominated by very few countries. This is problematic because make the market very monopolistic and unstable. For example, you can see in 2011 there were a rare earth crisis that propelled the prices of the ores to do the magnets at high prices. This is also important because the importance of this market in the future. If you can see, the growth is becoming exponential. Another issue that has this kind of magnets is the highly polluting mining that they suffer. Wait, sorry. You can see in the image the largest rare earth mine of the world in China. You can see the long residue tons of mark with a star. So we need to create, we need to design new materials in order to diversify the market, to make it more stable. And this is when where Passenger Projects enters. It's a European project which objective is substitution of permanent magnets that goes in the energy around 40 to 90 kilojoules per cubic meter. The project is mainly focused on manganese aluminum carbon and improved ferrites. For more information about ferrites, you can see the talk of Adrián Fernández at 1:45 p.m. So then, why manganese aluminum carbon? You can have manganese aluminum carbon has only one ferromagnetic phase that is metastable and can suffer a decomposition in beta phase or gamma 2 phase. But what are the properties that we want to that make it special? First, has a high theoretical Bx mass, around 12 megaoester. Also has a very low density compared to other magnets, around 5.2 grams per square meter per cubic meter. The material doesn't need a protective coating because has a good corrosion resistance. And finally, the material is cheap compared to normal rare earth magnets. So how we produce? In the project, we are in contact with a company that creates the main alloy through a casting. First, they mix the material in the correct proportions. They melt it, they pour it in a mold, and they let it cool down. After it's cooled down, they hammer it until they obtain a powder. The size of one cast is around 10 kilograms, so it's already a good amount of material. The powder precursor that they produce are in two sizes, below 90 microns and below 300 microns. This powder is sent to IMDEA Nanociencia and MBN, another company that we work with, and is suffer a process of milling, high energy ball milling. First, in IMDEA, we did with our method, and then the company used their own high energy ball milling method to produce effects on the sample. And finally, we did an annealing in nitrogen flow to recrystallize the sample. First, you can see the precursor that produces LCM is almost pure tau phase with only a bit of gamma 2 phase. But the problem it has is that the magnetic properties are not good for a permanent magnet, because even it has a good magnetization, the coercivity and the remanence are too low. So in order to enhance these properties, we made a milling, and as you can see, for the broadening of the peaks, we are creating a microstrain inside the sample. We are reducing the grain size, and also we are amorphizing the crystals. This has the effect, for example, the amorphization reduces the magnetization, but this reduce of magnetization came from with an increase on coercivity due to the microstrain and the grain size modification, increasing more than 2 times the coercivity. This creates an effect because the remanence is a competition between the saturation and the magnetization saturation and the coercivity. This competition makes first the remanence to increase and then to start to decrease when the saturation loss is too high. As you can see, after you anneal the sample, the crystals, the sample recrystallize, the annealing recrystallize the samples and also relax the microstructure. As we said before, the tau phase is metastable, so after the annealing, a new phase emerges, that is the beta phase, that we can see in blue. This phase will have an important contribution after in the magnetic properties. As you can see, the annealing recrystallize the tau phase, so we recover the saturation of at the start, but we lose some remanence, some coercivity. Sorry. This came due to the relax of the crystalline structure, reducing the microstrain. But as the presence of the beta phase increases, we can also see that the loss on coercivity is not so high to get the first results, resulting in a higher remanence at the end. If we compare this with the results of MBN that receive also a precursor powder from the same company, with the help of IMDEA, we can see that the milling produce almost the same kind of response of the powder, we lose some magnetization, but we achieve much more coercivity, increasing by more than 4 times. This is very good, but you can see that at the end of the milling, the coercivity seems to stop the increase. Coercivity gets reduced, but we don't achieve this saturation that we achieve when it's just mill the sample. Finally, the mix of summary is that we successfully produce almost pure tau phase powder in an industrial setting. That with IMDEA's flash milling method, we achieve an increase in coercivity higher than 2 times, while preserving a high remanence. And also with the NBN high energy bore milling process, we successfully show that we can produce the same increase, even 4 times increase of coercivity in a pilot scale plant. And this is a work that will allow us to see the way to create a industrial production of manganese aluminum carbon. I want to thank my group of permanent magnets and application, and thank you for your attention.
Thank you, Jorge, for a very nice presentation. Very sorry for the trouble with recording. I think we had some problem with the connection to the cloud. So sorry for that, because for sure it was a bit annoying. Do we have any questions? Maybe I will start with one. For the XRD characterization, did you use, what data treatment did you use? Did you refine the data somehow for the characterization?
Yeah, I don't have here the data, but we did a readable refinement with full prof in order to see the crystalline size and microstrain, but I don't have the data here.
Okay, because I was wondering that sometimes it's difficult to distinguish with the broadening of the peaks, no, with the microstrain and some effects that they appear in the crystal structure and with the size of the crystallites. But of course, yes, if you did the refinement, then it's giving you more information.
Yeah, right.
Great.
Yeah.
Thank you for the very nice presentation.